Hey everyone, today you will be learning about series convergence, or at least the first day of learning about series convergence. This lesson, if I can get my pad here to work, will be about maybe day one of this series convergence. Your textbook covers this in a different order than we're going to be learning about. So series convergence in our current textbook starts in section 9.4 and goes through section 9.5. So when you're looking for it in the textbook or when you're looking at page numbers, this is where the majority of the work will come from, just so you're aware of how it works. Okay, so first we want to review a little bit about what series are, so what an actual series is, and what it means for a series to converge. So something that's written in this format, so remember that this is a sigma, so this is sigma notation, and when you see something like this means that you're going to add a bunch of things together. So the way this one is written, what you are adding are all of the terms in the series. And again, a series is literally adding things together. So this says to go on for forever. So when we write out all the terms, we have first term, the second term, all the way. Then we will sometimes say, well, we have the nth term, and then dot, dot, dot. And all of this is to represent an infinite series. Last year, when we would talk about infinite series, and we talked about them just a little bit, you would, to figure out the sum of an infinite series, which I know sounds kind of strange even to say, but when you would find the sum, what you would do is you would consider the sequence of partial sums. So there were certain situations when a series would have a sum, okay? And when we looked at them last year, we would look at the partial sums, meaning we look at a combination of what the first sum looked like, what the second sum looked like, and as many as we needed to figure out if the series actually did what was called converging. So if you were to look at the sequence of partial sums, you would start off by looking at the first sum, which would just be the first term. And then you would look at the second term, which would be the second sum, which would be the first term and the second term. And you would keep looking at as many sums as necessary. So this would be considered the nth partial sum. And this would be comprised of all of the terms between the first term and the nth term. And you would basically look at all of these and determine if the series was approaching a finite sum or not. So then, again, let me repeat this. A series is really just a sum of a sequence, so adding up a bunch of terms together. If the infinite series represented in this form is going to have a sum, the nth partial sum would be given by that formula that we just had. So S sub n, first term, second term, third term, all the way to the nth term. And this would be, again, the nth partial sum. If the sequence of partial sums converges to a value. So as you look at each separate sum, if you notice that there's going to, like it appears to be approaching a certain sum, then we would say that the series converges, kind of like we did with our integration last chapter. Big deal, we're going to be looking at limits here. So the limit S is called the sum of the series. If the nth partial sum diverges, meaning it's getting bigger and not approaching one specific value, then the series itself, the whole entire series, is said to diverge. So we're going to start off today by reviewing two types of series that we learned about last year, and then we'll use those two types of series to talk about other series. So one of the series that you talked about last year is a geometric series. And a geometric series is a series, notice it says 0 here. It could also say 1. It could actually start at whatever value we wanted. But it takes on this form where you have the sigma notation, n starting at a value going to infinity. Then you have a, so some number a, times r to the n, and r stands for the ratio. So if the ratio is less than 1, then the series is said to converge to the sum, and we have a formula for this sum. You learned it last year. So the sum would be written as S equals, then we would say A sub 1, or A probably in this case, first term over 1 minus the ratio. So this is the first term of the series, and then R, of course, stands for the ratio. If the ratio happens to be greater than or equal to the 1, then the series is said to diverge. So the majority of what we're going to be talking about here is determining if the series converges or diverges. There's some things that you can do with series as we move forward, especially in the world of engineering, that you would need to understand the convergence or divergence. And just like we talked about last chapter, knowing that is helpful. And then you can determine what it actually converges to if you need to. But for now, we're just worried about, does it converge? Okay, so here are two examples of geometric series. This one you could rewrite if you wanted to as 3 times 1 over 2 to the n. So since the ratio happens to be a half, so here's the ratio right here, and a half happens to be less than 1, that means that this series converges. Now, since this is a special type of series, we actually know what it converges to. It converges to the sum of the first term, and the first term is found by putting 0 in for n. So you want to do it here, you could put 0 in for n. You have 3 times 1. So the first term is 3 over 1 minus the ratio, and the ratio is a half. So we now have that the series converges to the value of 6. By the way, if you were a little concerned about what type of series it is it geometric and what is the ratio, you are welcome to actually put the values in. So like actually put the n values in and come up with the terms. So you know that the first term is 3. If I put 1 in here, I get 3 halves. I put 2 in here, I have 3 fourths, and so forth. So you can see that the values are getting smaller, and they're getting smaller by a factor of a half, so therefore it will converge. All right, so this one now is also a geometric series. The first term in this case actually happens to be 1. Write that up here. And then the second term is 3 halves. And then the third term is 9 fourths. You can see that the series is growing, which means it won't converge. But if you're not 100% sure, you need to, again, compare the ratio. And the ratio is 3 halves, which is clearly greater than 1. So this series diverges. Okay, moving on, we're going to talk about another type of series that you learned about last year. It's called a telescoping series. So a telescoping series is a series whose partial sums, meaning you look at the first sum, the second sum, the third sum. So parts of the partial sums will cancel each other out. Think of like the telescoping making it get smaller. You will use the limit of the simplified partial sums to find the convergence for the series. So this is our first telescoping series that we're going to look at here. So we're going to actually write out all of the terms. I'm going to write them out in one long line. Last year, we probably wrote it out as sum 1, sum 2, and so forth. We're just going to write it in one long line here. So the first sum is when you put 1 in for n. So I have 1 minus a half. And then the second sum is when you put 2 in, and so I get a positive a half minus a third. And then the third term is what you get when you put 3 in there, and you get 1/3 minus a fourth. And you can see that we're going to continue in this pattern, and these kind of terms in the middle are going to cancel each other out. So we could actually write a formula for what the nth partial sum would be. So S sub n would be, this 1 is always here, minus 1 over, and you want to compare this number to what sum number you are on. So this was our first, second, third partial sum. And that was found by doing n plus 1. So this here would have been like s of 1, then all of this is s2, then all the way to here is s3. So this is our nth partial sum formula. Try to scroll here. Okay, so hopefully it makes sense to you that if we were to take the limit as n approaches infinity of this nth partial sum, this thing right here, that limit happens to equal, ran out of space on my line, sorry. If I take this to infinity, this goes to 0, the limit is equal to 1. So that means that the series, because it's approaching that finite value, converges, and it happens to actually converge to 1. All right, so now we're going to try another one. So this thing here, as you look at it, is not in a form that's you're able to figure out what the telescoping series is going to behave like. So you need to actually break this apart by doing a little bit of partial fraction decomposition. Everybody's favorite thing, right? So this is 2 over 4n squared minus 1. And that is equal to 2 over 2n plus 1 times 2n minus 1. So I'm going to break that. I'm going to go to the next line. I'm going to break that into two fractions. A over 2n plus 1 plus b over 2n minus 1. And then we're going to simplify this, and it's going to end up equaling 2. So when I get rid of the fractions here, I have 2an minus a plus 2bn plus b, and that whole thing equals 2. So I am now going to combine my n terms, my constant terms, and set them equal to the other side. So I have 2a plus 2b. Those are the end of the first terms. And there is no end of the first term, so 0. And I have negative a plus b, and that whole thing equals 2. This should all look familiar, right? So I need to do something so I can combine like terms. So many different ways to go about doing this. I'm going to multiply this bottom equation by negative 2. So I get negative 2a plus 2b equals 4. I'm going to leave the top line alone. And I get 4b equals 4. So b equals 1, which means by using the second equation here, a will equal negative 1. Okay, so now I have to actually rewrite this. And I'm not actually going to integrate it this time. I am going to use this as an actual sum and find the partial sums of the telescoping series. So rewriting it, a is equal to negative 1 and b is equal to positive 1. Is that right? Yep, I think so. Okay, so now I have negative 1 over 2n plus 1 plus positive 1 over 2n minus 1. And I'm just going to start coming up with the partial sums. So when n is equal to 1, I have, let's see, negative 1/3 plus 1. And then when I add on the next term is when n equals 2, and that's going to be a negative 1/5 plus 1/3. And then the next term, when n is equal to 3, will be equal to negative 1/7 plus 1/5. All right, hopefully that's enough. You can do as many terms as you need to help you figure it out. All right, so I'm going to see what cancels out. So again, this would basically be equal to the third partial sum. So my 1/3s are gone, my 1/5s are gone. And it looks like I'm left with 1 minus 1/7, which could be rewritten as 1 minus, and I want to think about this was the third sum. How am I getting 2n? Sorry, how am I getting 7 out of it? Well, I'm getting that by taking the 2n plus 1 portion of the problem. and I take the limit as n approaches infinity of 1 minus 1 over 2n plus 1. This happens to equal 1. This is the sum, and this is what it converges to. Okay, so as I said before, sometimes, a lot of times, we're going to have series that you don't really care what the actual sum of convergence is. You just want to know if it converges, or even want to know if it diverges. Either thing, right? So we want to talk about a couple of different rules that we're going to be applying as we move forward. So here's the first one. This one is the limit of the nth term of a convergent series. Okay. So I'm going to just write some things down. We're going to do a couple practice problems and then take a look at where we are. So this one, you're going to talk about what happens if a series is known to converge. So if the series, just call it a sub n, goes from 1 to infinity, if this thing converges, so if you know that the series converges, then the limit as n approaches infinity of just the a sub n portion of the problem will equal 0. So the stuff after, basically the stuff after the summation notation, that limit will equal 0. So if you know it converges, and I keep saying that because it's a big deal, if you know this thing converges, then the limit will equal 0. Okay. And kind of the other way it works, but not quite. If you have this series, infinite series, that does not, so if you have this series, and if, I guess I have too many ifs, if the limit as n approaches infinity of a sub n does not equal infinity, then the series diverges. Okay, so there's two things that are going on here. If this thing converges, then the limit must equal 0. If the limit equals 0 does not mean that it converges. And if the limit down here does not equal 0, then the sum actually diverges. All right, so let's see if we can put that into action here. So I have these three problems here. And we're going to use, let me go back a screen for a second again. We're going to use this nth term for divergence on all three of these to see if we can make sense out of it. Okay, well, we'll see what it means if this happens, but this here is the big focus of the next three problems. So if you're looking at something and you think that probably doesn't converge, then a fast way to check that is to just use the nth term for divergence, the nth term test for divergence. So you just take the limit of the stuff that's inside, so 2n over 3n plus 4. This limit, going back to last year pre-calculus rules, powers are the same, therefore the leading coefficients are the limit, 2/3 is the limit, okay? The limit is not equal to 0, which by the nth term test for divergence means that this series diverges. We're going to learn a lot of tests, so you want to make sure that you name the test as you are working through the problem, or answering the problem, I guess. Okay, so that's the first one. Second one, just as easy here, the limit as n approaches infinity of 5 to the n. Clearly this thing diverges. This thing is growing. It's an exponential function here. It is clearly growing. The limit is equal to infinity. So this thing clearly diverges by the same test. Okay. This one here, this one's one of our favorite because we learned this one in the last chapter, but we did it with integration. 1 over n, it's the same kind of function as 1 over x, and it has the same issues as 1 over x does, but unfortunately, our nth term for divergence does not work on this problem here. So if you were to take the limit as n approaches infinity of 1 over n, this limit equals 0. Doesn't really tell us anything because we know that if this thing converges, the limit will equal 0. But if the limit equals 0 does not necessarily mean that the function converges. This thing actually does diverge. We're going to learn about why in a second. But with this test, it's just inconclusive. So you can't really say anything else about it as of right now. Okay. So to keep you, out of suspense, we're going to go ahead and talk about why it actually diverges on the next screen here. But hopefully you'll remember as I start talking about it, because we did just take a test on this rule a few days ago. Okay, so you've learned a test for divergence, and you've learned that geometric series converge if the ratio is less than 1, and you learned how to find convergence of a telescoping series. Now we're going to talk again about our favorite series, the P series. Okay, and the P series is just the same here as it was in the last chapter, except for talking about series instead of integrals. So if you have something that is 1 over n to the P, so we're looking at this power on the n. So in this case, it'd be 1 to the P plus 1 over 2 to the P plus 1 over 3 to the P, so forth and so on. And this is called, just as before, a P series, where P is a positive constant, so it does need to keep getting larger. Two rules about this series, and they're the same rules as last chapter. If P is greater than 1, then the series n goes from 1 to infinity, 1 over n to the P converges. So same rule. But if P is less than or equal to 1, then the same series diverges. So this rule isn't that much different. The only thing that's different is we're talking about series as opposed to integration. If P equals 1, which is what we just saw on problem number 3, the series would be 1 over n, and you'd have 1 plus a half plus a third, dot, 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 okay? This particular series is what's formed, and it has a special name. It's called the harmonic series. And I just point this out because I know I have a lot of music people in my classes. And this series, you should understand things about harmonic difference. I don't even remember the word now. Harmonic things that occur in music. And I just thought I'd point out where it comes from. So in music, this is one piece of it. Strings of the same material, diameter, and tension, whose lengths form a harmonic series, produce harmonic tones. Okay. So all of it is related. Any series that is of a form that's slightly different but close. So in this case, I'm going to write it like this. A n plus b is considered a general harmonic series. So if you had something like 1 over 2n plus 5, you would know this was a general harmonic series and it will diverge. Okay. If you see anything like that, you could call it a general harmonic series and know that it diverges and be done with the problem. All right, so we're going to do a couple here. This one, the first one, is written in terms of series, like with the summation notation, and this one is just written out in its terms. All right, if it helps, you might want to rewrite this, but you do not have to if you don't want to. So this can be rewritten as 1 over n to the 1/5. This is a P series, and clearly P is less than 1, happens to be equal to 1/5. So therefore, by the P series test, this problem diverges. Okay. All right. Next one. It's not really written in the same manner. So if it helps you, you can rewrite it so it looks like something that you're able to work with. So this is like 2 to the first times 2 to the 1/2, which would be 2 to the 3/2. And we have the same thing here. 3 to the first times 3 to the 1/2 would be 3 to the 3/2, and so forth. So you could write this in summation notation, and goes from 1 to infinity of 1 over n to the 3/2. And since your power is greater than 1, so p is greater than 1, it happens to be 3/2. this series converges by the p-series test. Okay, so moving on. So we're going to add a couple extra tests to it. And again, they should look awfully familiar. So we're going to talk about comparison tests again, but comparison tests for series as opposed to integration. So just like when we were talking about integration, there was some that were clearly able to converge and some that were not. So as we said I said a few minutes ago, we've had some that you already learned or reviewed. We've got geometric series, telescoping series. We talked about p-series. And not all functions are going to take on those forms, so we have to have other ways to handle them. So for instance, this first one here, this would be a geometric series with a ratio less than 1, so you'd be able to say that this converges. But this is clearly not a geometric series. So how do we handle it if it's not something that we know? And this one down here, this is clearly a p-series test, and its p value is greater than 1, so it would converge. This one is very similar, but not quite a p-series, so how do we handle it? So we have two ways of handling it, and again, there are ways that we have already talked about with integration. So the first way that we have is the direct comparison test. And the rules are the same as they were in the previous chapter. So if you have two series, okay, so the first one of them will be a sub n and the other one will be b sub n. And a sub n happens to fall between 0 and b sub n. So this has to be true. This is the comparison test. So if the sum from 1 to n of b sub n, so if the series represented by b sub n, the larger one converges. So if the larger series converges, then the smaller series converges. Okay, so if b sub n converges, I forgot my then the smaller series converges. And just like before, the opposite is true when you're comparing small to large here. So if the smaller series, in this case a sub n, diverges, so if the smaller series diverges, then the larger series also diverges. And just like before, last chapter, we're going to be comparing it to things we know that converge or diverge. So we'll be using things related to p-series, but we could also now use geometric series. So if we know that a geometric series converges, we could compare something to it. If we know that p-series converges, we can compare it in that manner. A limit comparison test, same rules as last chapter. So you have two series, they are both positive. And you can compare them. So if you compare a sub n over b sub n, or vice versa, and you get an answer, and L is finite and positive. So it cannot be infinity and it cannot be 0. So it's finite and positive. So between 0 and infinity, then both of the series behave in the same way. So they either both converge or they both diverge. So whatever you pick to compare, you have to know what its convergence is. All right, so let's practice a few. And again, I hope these will make sense to you because we've already dealt with similar cases. All right, so here I am looking at 1 over 2 plus 3 to the n. 1 over 3 to the n is a geometric series, and it would converge. So I'm pretty confident that making something bigger in the denominator is going to make the new thing converge. So we just have to write that out. So I'm going to start by doing how I have done in the past, but you certainly do not have to do it this way. You can skip this whole step here. So I know that if my denominator is 2 plus 3 over n, 2 plus 3 to the n would be greater than just 3 to the n, which means the reciprocal of that situation, 1 over 2 plus 3 to the n, would be smaller than 1 over 3 to the n. And this series, so I'm going to write it as a series, and goes from 1 to infinity of 1 over 3 to the n, converges, and that's because it's geometric. Okay. Therefore, our series converges by, and you're welcome to just say DCT. Okay, that's totally fine. All right. So now moving on to this next test, or sorry, this next problem. I'm going to use a different test on it. So when I look at this, I see 1 over the square root of n. And I know that that diverges by p series. So I'm guessing that just adding a measly 6 onto that is not going to change that. So I could do a direct comparison test, but I'm feeling like that's not really going to help because this thing here, the way it's written, would be smaller than 1 over the square root of n, and that doesn't tell me anything. That would be inconclusive. So instead, I'm going to do a limit comparison test. And I am going to compare it to 1 over the square root of n. And I know what that does. I have to know in my head what I'm getting out of this. So it doesn't matter which one you put in the numerator or the denominator in this situation. It should work either way. And I'm left with square root of n plus 6 over the square root of n. Both of these have the same power of a half. Since they have the same power, the limit would be the leading coefficients. So that happens to be 1. As long as the value for the limit we get is between 0 and infinity, my original function, or sorry, my original series and the series I was comparing it to, which was this one, behave the same way. And this one we know diverges by p series. So therefore, my lovely series diverges by LCT. All right, moving on. So this next one, I don't know if there's one way that's better or another with this one. I tend to do a lot of radical stuff with the limit comparison, but I think I'm going to try this one with direct comparison just for practice purposes. I'm looking at this and I see square root of n in the numerator and n squared in the denominator. I'm feeling like this is going to converge because the denominator is going to stay um, pretty big in comparison to the numerator. So we'll see what happens here. So I'm first going to start off with just 1 over n squared plus 1 being less than 1 over n squared. Then I am going to multiply the whole thing by the square root of n. And then, oops, I have too many pluses there. And that left side here, sorry, that right side is the same as 1 over n to the 3 halves. Okay, so what I have now compared my series to is the series from 1 to infinity of 1 over n to the 3 halves. This is a p series, and that p is greater than 1, so therefore this converges. So what I'm comparing to converges, and therefore my series of square root of n over n squared plus 1 also converges by DCT. All right, I think this last problem we can do without any of those rules that we were just talking about and just use a straightforward one from just a few minutes ago, or not even a few minutes ago, I guess maybe more than a few, the beginning of the video, that has to do with basic rules for divergence. So when I look at sine of 1 over x, I am feeling like, well, I know that sine is always between -1 and 1, but this is really the same function. I'm just taking the reciprocal of the numbers I'm substituting in, but realistically, this thing is still going to just fluctuate. So I'm not really going to have any value that it's going to approach. So before I do any complicated test, I think it might be best off if I just try the nth term for divergence. So I'm just going to test the limit as n goes to infinity of sine of 1 over n. And I know that as n goes to infinity, this inside part goes to 0. And I know that sine of 0 happens to be equal to 1. And if, according to the nth term for divergence, if my limit does not equal 0, then the series must diverge. So without doing a whole bunch of extra work, I can determine that this series diverges. All right, so hopefully you're not getting too confused yet. We will spend a little bit of time in class tomorrow going over some of these problems and some of your homework questions that you might have as we're working through it. Please make sure you're prepared to ask questions. See you then.